Okay, everyone, welcome to my channel. My name is Ryan Schul. In the narrative today, I want to look at a comparison of rules-based AI with transformer-based AI. So I'll try to cover this topic as best as I can. I try to put in like an A-level effort for all these things. I think some tend to come out pretty well. Some are fairly decent. Some are pretty awesome, I think. It never really turns out exactly the way you think it will, but still put in an A+ effort. So what is a rules-based model? Basically, you define a whole bunch of rules and you say, if this happens, then this is going to happen. If this other thing happens, this other thing can happen. Okay. So it gets very complex very quickly, and it's so many scenarios that can blow up. It's really hard to capture all of these using some type of if then, like it's very difficult, right? I think Siri was a first great attempt at doing rules-based AI, but it comes up quite short compared to the more modern transformer architecture that we're going to look at in just a minute. So again, Siri is more like it doesn't really learn semantics. It doesn't really learn sarcasm. It doesn't really learn like punctuation and emphasis and things like this. I mean, to a certain extent, but really very weak compared to a transformer, which can actually remember what happened in the past, right, and use that to make intelligent and informative decisions about what can happen or what should happen in the future. It's not really rules-based. It's much more content-based and much more sort of like a human would learn something and make a response or make a recommendation if a question was asked to a person. So transformers are quite evolved compared to a Siri type of rules-based system. So what I'm going to do is put together a few simple conversations here. So this is something that you might see from an Amazon product review. I love this product, absolutely terrible experience, not bad. Works fine. I wouldn't recommend this to anybody. Okay, so we're capturing some information. This is going to be the basis or the foundation for our analysis here. And I want to understand the labels. I'm going to say either this is great and fantastic product, or pretty much mostly great and it still gets a good label, or this was kind of a piece of junk and just total waste of time. So these are the two types of outcomes, right? So with the rules-based versus, which is kind of like a pseudo transformer, but transformers are much more powerful, right? Because it doesn't rely on the if-then kind of architecture. It's much more holistically understand the context of what's happening and then make a decision, right? So we have the, I'm just going to call this Amazon reviews. They're not really Amazon reviews, but if you go into the website, you'll see something very similar to that. So I'm going to have a dictionary of positive words here. Here's the key value pair. This is the key, this is the value. Okay, so amazing gets 2.4, love 2.5. So the higher the number, the better off, or the more positive, this is going to be in a positive context. But negative words can have higher or lower numbers too, right? So let me run this just to kick it off here. So something that's highly positive is going to get a high ranking, and this is going to be considered a positive experience, right? Something that's highly negative, like horrible, junk, something like this is going to be more emphasis, more strong verbiage, more strong words or adjectives, right? So the lower the number, the more neutral. In both scenarios, the higher the number, the more dramatic, I guess. So we have our rules down here, and we have a length of tokens. We're going to loop through all of these tokens, and also we have to make sure that these don't have like upper and lower and lower letters too. We want everything to be uniform and standardized. So punctuation should be handled, uppercase and lowercase should be standardized, right? We want like the same type of fundamental basis for all of this language to help the model to learn better and make better predictions too. So this is a pretty standard rules score. I created this UDF. I think I might have actually found this online. Basically, just taking all of these words, tokenizing them, which means creating the word into some type of mathematical representation of the word. So basically, converting words into numbers, and then the rules-based system can analyze these numbers. So the computer, in this scenario, in a rules-based system, and a lot of these more classic types of models, like overheat and drain and waste and scarcity, extremely, that has no meaning whatsoever to the computer, right? You have to tokenize these words into some type of numerical, mathematical representation. Then you can feed that into the model, and then the model can start to make predictions. So we set up the model, ran it. This one I'm using, let me see, what kind of classifier? It should be looking. Maybe it's over here. I think this is it, right? I'm not even using the classifier in this case. Okay, so I did this code about a week ago, and I was busy with a few things. I got sick, so I'm just doing the video. So this doesn't even have a classical sort of classification model in it. It's just doing some basic rules-based labeling of the data. So we have overall prediction 100%, so that's pretty good for the ones, right? For the zeros. For the ones, it's closer to 82% accurate or precise, right? Here's the recall. So higher is better. You want this to be close to 1.0. So in this case, this is 100%. This is 86. 86 is pretty decent. Closer to 1 better without overfitting the model. So you have to be careful of overfitting too. That's a whole different topic. I'm not going to get into it now. I have other videos on my channel about overfitting or underfitting, so you can take a look at those if you want. We're not going to go down that whole path because these videos would drag on for hours and hours. I try to create one topic and just focus on that topic and not go off on some big tangents. So this looks decent, 92%, 93%. And overall accuracy, 94%, 93%, 93%. So pretty decent first go at it, right? So pretty happy with those outcomes. Let me go ahead. This is doing a, okay, so this is a BERT. So this is more of a modern type of transformer architecture, right? So there's actually over 2 million models out that these guys have put out. It's pretty remarkable. Now it might even be closer to 3 million. You can copy and paste this link and take a look at all the updates on their website. So what are we looking at here? 2,089,000 models. So it's pretty extensive. You would just do a search over here by model name or model type. We're working with text-based models, and we're trying to make predictions based on English language. So use common sense and use judgment when you're looking for the type of model that you want to use. I am using this is BERT. So BERT comes in right. Where is it? I was seeing that. Oh, BERT prediction. Okay. So we're looking at the text column of the data frame, right? The data frame is this over here. You can see the data frame. We're looking at this column in this data frame. This is called dataframe.head, and we're looking in this column. So we're taking this BERT model and scanning it over all these variables, right? Putting this into, getting this from a list, right? Because it's actually a data frame. It's a column in a data frame. Put that into a BERT prediction and then print BERT scores. Okay, and this was actually the model I picked. So again, you have to kind of search around a little bit and see what is going to be good for you and see what's going to work in your environment and your setup. Yours is going to be slightly different from mine, but that's fine, right? It's kind of like a hunting, pecking exercise. You have to try a few different models, see what works. Go with it. If it doesn't work, then try a different model. If that doesn't work, then try a different one too, right? So you have over 2 million to pick from. But some of these obviously are not going to work in this kind of scenario, right? Like we have a text-based transformer model that we're looking for. So I'm not going to pick a financial model. I'm not going to pick some type of, what else? They have all kinds of things on the site, right? I'm not going to pick some kind of Tencent, Hunang, like that just doesn't make sense to me. I guess you could test it. It doesn't sound like it's gonna solve the problem. So you would just search for a model like English. And it kind of guides you too, right? So it kind of like auto-completes as you start typing English, embedding small English. So this might be another one that you could try, just for instance, right? And you have the details of the model over here. And where's the model name? I'm looking for that right here. Okay, this is good. So yeah, at the bottom they have more documentation about how the model would work, and this is actually called model and code, right? Where's the model? oh, this is sentence transformer model path. Okay, so that's just a different type of model, different name. You would feed this text from the data frame, and here, this is assigned to your model, and you're good to go. So in this case, we have 0.933, 0.933, 0.933 is across the board. So pretty decent performance. It fluctuates a little bit lower than this, but definitely higher than this. So it's kind of a little trade-off, but this one ends up with 0.933. So these two models perform fairly similar, right? It's pretty consistent between the two. So either one is going to give you a decent performance, but I bet we can actually get this even more accurate, right? So the BERT model looks what was I gonna say? Potentially optimistic. It came up with actually like the same ultimate score as the rule-based model, right? So I think we can do better. So let's test a different model over here. So now we are using, let me find the model here, give me a second. CMP, okay, rule-based, but I think it's coming from, oh, I see, okay. So we're comparing the rules-based model to the BERT model. That's what this is doing over here. Again, I wrote this code like a week ago. I was a little bit sick for several days, or I didn't do anything, so I'm just swinging back to this right now. So there's the rules-based model and then the BERT prediction model. We can compare these side by side. Okay, and here is the ultimate score, 0.933. We just kind of sort that. So this is maybe just slightly more accurate, but negligible. I mean, I don't think it's going to make much of a difference. The transformer is right and the rules are wrong. So the only thing I liked was the color. The label was 0. The rule predicted was 1, but the BERT predicted was 0. So here the BERT outpredicted the rules-based model. Here's an example where the rules are right and the transformer is wrong. So customer support solved my issues. The actual label was 1. The rule-based model predicted 1 and BERT predicted 0. Okay, so this is kind of like a give and take here, back and forth a little bit. But you can see overall they're pretty close, right? So in this case, I would probably go with the BERT model. It's a transformer. It's not rules-based, although the performance is pretty similar for both of these. So I think we should keep going and look for a model that can outperform either one of these. I think we can get there. So the outcome is very close in overall performance. This is clear and concise, runnable. A/B tests, you see what happens before, you see what happens after. I kind of like these A/B tests. You see these all the time at Facebook or Meta. Now it's called Meta these days. So super popular over there. I like it. I think there's a place for these things. I interviewed for a couple of jobs where I would be doing A/B testing all day long, and I couldn't see myself doing that. I think there's too many multifaceted things in the machine learning world just to focus on nothing but A/B testing day after day after day. So I said no to that. But anyways, there is a time and a place for these things. So the lightweight ML, classical ML model, bag of words, n-grams, and rules-based lexicon beats the rules-based by a lot, and it's fast. And you can see the time over here, the time to completion, 8.1 milliseconds, and the transformer took 2,987 milliseconds. Okay, so really, probably in large data sets, you would actually go with the rule-based model, but nowadays it is, what is it, September 14th, 2025. Nowadays, the transformer has evolved to a state where really they should be able to crush any kind of rule-based model. So let's keep going and look for a solution that can provide even a more accurate outcome. So we have TF-IDF. This is text frequency, inverse document frequency. This is classic machine learning architecture. And we have a couple different models that we are referencing over here. VADER sentiment. So a sentiment is like a feeling, positive, neutral, negative, things like that. Here comes the cat. The cat is going to have an opinion too, I guess. Okay. What would you go with, cat? Transformer? Yeah, me too. Okay, so let's create some Yelp Polarity. The last data set was kind of small. I forgot how many we had over here. But this was it. We had like maybe 30 something different comments that we got, again, from this Amazon. I'm just saying it's Amazon, quote unquote. It's not really Amazon, but you know, if you look on their website, it's going to look something like that. So I think honestly, I think that was kind of a problem why the two models came up pretty similar, because these transformers want lots and lots and lots and lots of data to make really intelligent decisions, right? If you give it 30 data points, it might come up short, and that's what we're seeing here. So I'm thinking if we get, let's see, this is coming from Yelp. I want to create 8,000 scenarios or 8,000 different reviews. This is going to be a Yelp review now. And look at the text and the label. So we're looking at text polarities. I'm sorry, Yelp polarities. So positive, neutral, or negative. The text. So what are people saying about their experience in different restaurants on this Yelp data set? And then the label of the data, is it can be a 0 or a 1. Remember, we want to match these labels, positive or negative. So we want to look at the polarity and then the text and then the label as well. So I think this ran, we got our 8,000. And you can test this with as many as you want, right? You can put this up to 80,000 if you want. It's going to take longer to generate all the Yelp reviews, and it's going to take longer to do the analysis, but you'll get even more accurate results. And in a large data set, even 8,000 is probably going to be pretty small here. Like in a real data set, if you're doing this for a real corporation, you can have hundreds of thousands, even millions of records that you're trying to analyze. So as you get these massive data sets, the transformer model should perform better and better and better. So the accuracy is 0.70, so 70%. This is the classic TF-IDF. 0.89, here's 769 and 0.89. So good outcomes, 0.89, definitely good. 0.70, that's a little bit light. That's 70% of the time it's correct. 30% of the time it's not correct, which is a little bit of a concern. Here we see the confusion matrix. So we want this number to be high, this to be low. We want this to be close to 0 and this to be close to 0. So these on the northwest and southeast should be higher and higher. The northeast and southwest should be lower and lower. And if you take a look at confusion matrix, you see the true positive, true negative. Show you real quick. Okay, so here's an example. Let me see what they're saying. Okay, so true positives, true negatives. That means the model picked positive and actually it was true in that case, or the model picked a negative and that was true. If you have false here, so northeast and southwest are always falses, then the model is not learning all the nuances or the details that it should be learning, right? And it's making some mistakes. So you want again, the northwest and southeast to be higher and higher, as high as positives, and the northeast and the southwest to be as low as possible, right? So closer to 0 is better. Here's the output, so we can just have a quick sanity check. I'm not going to go through all the details right now, but you can take a look at your leisure. So so I think we're headed in the right direction. We have a sentiment analyzer that we can take a look at here and see what the output is for these guys down here. Okay, we know that any kind of accuracy, 0.70 is okay, but again, higher is better. We want this to be like 85, 90, 95, closer to 1.0 is better. If it's 0.71, 71% of all the labels were correct, but 29% were not correct. So 29% of the time we're making mistakes, even though 71% of the time we're getting it right. So again, that's good. We're taking a good stab at it. But even with this VADER model, which is a different version of the machine learning model that we saw before for text analysis, again, good, but I think we can take a couple more passes at this thing and make it even better. Let me get a sip of water here. Okay, so here's the final output of the VADER model, 0.70, 0.77. So again, I think we're heading in the right direction, but we still have to keep going. These models at 70% accuracy are not doing what I would like it to do in the year 2025. Now, if this was 10 years ago, I would be thrilled. This would be fantastic. But we have evolved from something that's somewhat primitive like this into something that's highly sophisticated, like I will show you in just a moment here. So Control Enter to run the next cell. So we have our X and Y's doing all the training for the data set. Again, looking at Yelp. The training and the testing are set up here. Basically training, I'm not going to go into a big explanation or description about this thing, but The training set is usually 70 to 75%, and then the testing phase is how accurate does the model make predictions against actual labels that have already been predefined and compare those, right? So the training is basically, if you're in college or high school or even middle school, you go to class, you do the homework, that's your training phase. The testing phase is when you sit down and take a test, right? And show the teacher how much you have learned, or maybe how much you have not learned. Hopefully you've learned a lot. So here we have TF-IDF vectorizer. So again, taking all the words, vectorizing these, right? So it's a numerical form of the word, and everything is converted to a mathematical representation of the word. Then the computer can do its analysis and start to make predictions. So if the computer just looks at things like I showed you originally, these words mean absolutely nothing to the computer, right? It has no idea what's a masterpiece, what a masterpiece not. Battery life outstanding, charge fast, 2. Computer has no idea what this is, right? But when you vectorize it or convert it to some type of combinations of numbers, then the model can understand that and make predictions, right? Training and testing make predictions. So now with the TF-IDF vectorizer, we get 92% accuracy. So now we're definitely seeing a boost here in performance. 92% of the time, the model is making correct predictions. However, still 8% of the time, it's getting it wrong, right? So I think we really have to pick a different type of transformer, much more modern, like ChatGPT, for instance. We're not actually going to use that in this case, but something somewhat analogous to that, right? Use a real transformer model, go ahead, rerun the analysis on a fairly large data set, and then see how well this model can compare, or see how well it can produce results that compare to what we've seen previously. Okay, so there's a few things that we are running through the model. This is just pretty standard stuff. All this is the Yelp Polarity, and remember, this came from originally back here. So we have these 3 columns, Yelp, Polarity, text, and label, and we have 8,000 records that we're looking at. That is analogous to this over here. Okay, so just keep that in mind. But in this case, we only had about maybe 30, give or take. All right, so pretty small data set. I want a bigger data set, and I want a more sophisticated model. So fast forward to this. Okay. And again, I'm going to save all this code and give it to you guys. I can actually download this right now. I think it's already been saved. 19 hours ago, it was saved. Nothing's really changed here. So let me save as HTML. I will download this file, and when I post the video later today, I'll post all the code so you have all the source code too. So again, it's a very similar kind of thing. We have the data frame with a couple different columns, the Yelp Polarity, the text, and the score. I believe that's what it was, right? Okay, so we're feeding these models in. This is the tokenizer right here, again, converting the words into numbers. And we're using auto mode for sequence classification. That's the model right here. So this is the tokenizer, this is the model. And if you follow this down, you can see how this cascades and flows down. We are doing a loop here for KV in model ID labels. So anytime you do a loop, you're iterating through all the different items in the data frame over and over and over, and doing the training testing phases of this process. And then we will collect the output in just a minute when this finishes up. So that's the model, and this is the tokenizer. If you do Control F or Control C, Control V, you can paste that, and you can see how these things flow down here. So we have the tokenizer down here. We have the model down here. Where did it go for mod? Eyes are going to be so bad. I'm going to need glasses like super soon here. MDL. Oh yeah, here it is. So we're tokenizing it, running the model, and fetching the output, and we're looking at the sort of like the analytics of the output, the report, and basically quantifying how accurately this model is able to make predictions. Okay, so that is the goal here. It looks like this is still running. Let me just take you through my notes while this finishes off. So the architecture for Siri basically uses a hybrid pipeline of Speech to text. I remember this thing back in the day. You would just talk into it, converts the speech to actual text. I'm sure it vectorizes that text. It has to do that at some point. And then it's going to use rules-based modeling to try to generate a response or a recommendation based on what you say to Siri, right? I've never owned an Apple product in my life, but I remember people using these things, and that's what my observation was. So I like to put these types of characters on here. And the limitations, of course, like I alluded to before, relies heavily on rules-based architecture, and it doesn't generalize very well because of that, right? So you have the context handling kind of weak. It doesn't really remember things. It doesn't really understand the context of what's being said, and that was a big limitation. Performance was scattered and kind of fragmented at best. Different models were tested and tried, but always the limitations were the same. Like it can't remember anything, with a couple of small exceptions, and doesn't understand the context of what's being said. Thus, the accuracy was at the time it was okay, but by today's standards, it kind of sucked. Okay, so transformer like GPT, BERT, there's a bunch of these different things at this point in time. So they really use large-scale pre-training on massive text corpora. Corpora is a body of text, so these could be easily millions of columns of data, could be billions actually. So it's pretty comprehensive in terms of the scale of what these things can learn. And then based on all the learning, the training and testing, like I just showed you, it's going to make predictions, right? And these predictions will be fairly accurate and quite impressive, actually. So they learn the context, they learn embeddings, not just keywords, and they can handle new phrases that come up, things that's never seen before, right? Because it learns more like a human, very comprehensively, very holistically. Accuracy and flexibility of transformers really outperforms the rules-based pipelines by understanding the actual language, handles ambiguity pretty well, and it maintains the context of the scenario, of the question, of the recommendation, and things like this. Okay, so Siri started as a rules-based heavy classification system. Back in the day, it was decent. By today's standards, it's not impressive at all. Transformers really were more accurate. They understand language, context, generalize much better, and don't depend on rigid templates or some type of rules-based architecture, right? Siri has improved with neural networks, but the early design decisions made it very limited in what it could do. It's not like, okay, let's start small and just scale up. Like it was never designed to evolve into a transformer. The whole concept was just totally different back then. Again, I think at that point in time, that was pretty brilliant, but we've come a long way since then, right? So today's transformer architecture is really far and above anything that we saw in the past decade or so. So anything from Alexa to ChatGPT to BERT is really going to knock these rule-based systems out of the water, and that's where we are today. Okay, so this finished off, nice timing, very nice, because I just finished off too. So the accuracy for the rules-based system was 0.736 for the transformer, 1.0, so perfect for the transformer, 1.0 for the transformer. Rules-based F1, 0.79, again, we want higher is better, 1.0 is great, that's perfect. So the transformer got 1.0, transformer 1.0, so yay for the transformer. Latency, pretty fast, these things run pretty fast, because again, it's just applying simplistic rules to solve the problem. The transformer is going to take a lot longer, but look at the results that it spits out. It's way more accurate. So the rules-based, 73% accurate, or the accuracy for the F1 score, 79, over here, 100% accurate, right? So here's the confusion matrix for the rules-based system. So again, you want this to be higher, this to be higher. You want these numbers to be pretty low. So Northeast and Southwest, pretty low. For the rules-based system, exactly what we'd expect. It's making pretty good predictions, fairly accurate, good F1 score. We just saw that right here. But still, this is 79% accurate. 21% of the time it's making mistakes. With the transformer architecture, we have our Northwest and Southeast 254, 256. The Northeast and Southwest is 0. That's exactly what you want to see, right? So this system is learned perfectly. In the next box here, you see the same thing. So this is a threshold of 0.5. This is a threshold of 0.20. And then it spits out this for a quick sanity check. So that's it, guys. That's how you compare rules-based AI with transformer-based AI. Hopefully this was insightful and informative and shed some light on a topic that I think is pretty interesting. I just want to introduce you to that, you guys to that too. Again, I'll share all the code when I post a video later today, so you can copy and paste this, run this in your own Jupyter notebook, and have fun with it. And then by all means, try to feed in your own data set. Get another data set that you see online, substitute that for this right here, put that into a data frame, run it just like I showed you, and then you can feed in any data set, right? This is not just like, okay, it only works in this specific data or whatever. No, it's going to work in any data that you feed into it. You just have to have the setup right. So I set mine up as a data frame. I love these data frame objects. I use it all the time. So this is my go-to for all these things. So it's set up as a data frame. Just convert your text to a data frame. You have everything you need. You can run it out of the box. So that's it, guys. I think I saved this down. Let me look at my downloads folder. Yeah, it's right there. Okay, so I'll load the all the source code with the video later today. Thanks for your time. I'm going to wrap it up here, and I'll see you guys when I post the next video. Goodbye for now.